Welcome back to Statistics. In this section, section 1.1, still in chapter 1, we are going to continue to look at exploring data, but we're going to start looking at analyzing categorical data specifically. In this section, let's talk about the objectives. You're going to construct and interpret bar graphs and pie charts, recognize good and bad graphs, construct and interpret two-way tables, describe relationships between two categorical variables, and we're going to organize statistical problems and how to attack them. Let's start with categorical variables, which we talked about in the introduction video, and that is individuals placing individuals into one of several groups or categories. The values of a categorical variable are labels for the different categories. If you look in the chart here given, you've got different types of music. We've got adult contemporary, adult standards, we got contemporary hit, we got country, etc., etc. And then this is the count of number of stations as you go down, with a total of 13,838. So what we're going to do is we're going to break this down. Here's our variable. It's the format. And then what we're going to do is look at the count of stations. So there's 1,556 adult contemporary out of 13,838. We can also look at that as a percent. 1,556 divided by the 13,838 is 11.2%. Then you got adult standards, which is 8.6, 4.1. In a lot of cases, the percent makes it a little bit easier to do a little comparison. So quickly, I can look at this and go in the percent or the relative frequency table. And when we talk about relative frequency, relative means percent. Converted into percent. Frequency just means how often. See, this is a frequency table, but it's specifically dealing with numbers, whereas this is dealing with the percent of stations. And I can quickly, here this doesn't tell me much. I can say, well, which one has most? Okay, this one does. But I can look over here and start to compare better in terms of percent. But then you go down to this, shouldn't this be 100%? So people look at this and go, well, something's wrong because this is only 99.9. Where there's something that we call round-off error, where these round off, and in the end, this is 99.9. If we would have been a little bit more accurate and gone out to 2 decimal places, well, then this would be even closer to 100%. So don't worry about that. That's just called round-off error. We need to define how to display categorical data. Okay, here we go back. We got the format of the station and the count of stations, just like the last slide. What we're going to do is we're going to break that into a frequency table. How often does it happen? Now notice here you've got categories: adult contemporary, adult contemporary hit, you got country, you got news talk, you got a lot of different options there. And these bars are not touching. Because we got categorical variable, we're talking about a bar graph. And people think a bar graph and a histogram are the same thing. They are not. A bar graph deals with categorical data, where a histogram deals with quantitative data. There's always space in between when you're dealing with a bar graph, because you're dealing with these bars don't need to be touching, because it doesn't make sense to have these touch, because we're breaking it down into categories. But then along the y-axis, we're still getting the frequency as to how often it happens. If we wanted relative frequency, we could convert this to a percent along that axis as well. We can also break percents into a pie chart. We just thought we'd talk about pie charts. It deals with your percents here. Everything's broken down in percents. Although in statistics we don't really use pie charts very often, we would prefer that you actually do a bar graph of some sort. So we don't focus much in AP and statistics on the pie chart. It's just more you'll see it in the media, you'll see it in the newspaper, you'll see it in data that you might eventually break down. But again, here's your adult contemporary, your adult standards, your contemporary hit, and these are broken down into percent, so we have what's called a relative frequency. Something that we need to make sure we're aware of, and that is good graphs versus bad graphs. Bar graphs compare several quantities by comparing the heights of bars that represent those quantities. Sometimes we can be tricked into seeing different things, and we're all tricked, and it's tricked according to the eye. Here's a prime example. This is done by CNN USA did a poll that I grabbed out of offline. Question was, based on what you have heard or read about in the case, do you agree with the court's decision to have the feeding tube removed? This is about a young lady who was in an accident and she was basically brain dead. The husband wanted her to be pulled, the plug to be pulled after 2 years, and the mom and dad said, no, don't do it. So they took it to court. Well, CNN did a poll, and they found that Democrats versus Republicans versus Independents, that there was this big difference between the three in terms of whether you're Democrat and whether you agreed or not. However, so you look at this quick and you go, all right, well, that's a huge difference between those three. However, if we break it down with correct graphs, then what happens is you go, actually, there's really not that much of a difference here. What happens, we made it look bigger than what it was because we started at 53 in our scale, whereas here we started at 0, then 10, 20, 30. So this is an actual scale where this is a zoomed in version. And when you're looking at the newspaper or on the news and they quickly show a graph of something like this, you're not necessarily looking at the scale, you're just looking at the picture real quick going, wow, there's a big difference between the two. You want to be careful with something like that. We can all be tricked for something like that. For example, a Chevy Silverado versus a Ford F-150. They might on a commercial show this kind of graph real quick as to what the sales are like, when the sales are actually within 100 of each other, and it's really not that big of a difference from one year to the next. So just be careful. Some graphs, they're good and bad. Sometimes they can trick you. Then we get into something called two-way tables, literally two different things to look at. And those two things are a row and our column variable. And they're usually going to go through and tell you in the title. For example, here's some data. Young adults by gender and chance of getting rich. Well, chance of getting rich is our row variable. That's this. And then gender is our column variable, which is this, female or male. What are the variables being described by this two-way table? Getting rich and gender. And how many young adults were surveyed? A total of 4,826. Notice what we've done is we've added something in the margins that we call the totals. And if you add up the totals, 96 plus 98, a total of 194, figure there's almost no chance. 712, figure there's some chance. 1,416, 50-50 chance, etc. Out of the whole group, 2,367 were females, 2,459 were males. These two numbers will add to give you 4826, and all of these numbers will still add to give you that exact same number. But we're talking about totals, and that's where our marginal distribution comes into play. Here's the official definition of marginal. The marginal distribution of one of the categorical variables in a two-way table of counts is the distribution of values of that variable among all individuals described in the table. A couple of notes. Percents are often more informative than counts. That's key, percents, especially when comparing groups of different sizes, so that you're comparing apples to apples, because otherwise I don't know if we're talking about 10 people or are we talking about 50 people. That can make a difference. So in terms of percents, sometimes it's easier to look at it that way. To examine a marginal distribution, use the data in the table to calculate the marginal distribution in percents of the row and column totals. In other words, look at the totals and make a graph then to display the marginal distribution. Let's look at an example of the graph that we just showed you. You've got your female and male and then your chance of getting rich. Well, what we've done here is we're looking specifically at a marginal distribution here. 194, figure they had almost no chance. So 194 out of 4,826 gives us a total of 4%. So I go down here, almost none. There's my graph, and it's about 4%. Then I can do some chance. Well, looking at some chance, we've got 712 out of 4,826. That's what this is. And there's 14.8%. That's the graph for here. And this is going to be categorical, so it's going to be a bar graph because there's space in between, and these are actually categories along the bottom of the axis with our percent, so a relative frequency histogram up the y-axis. And we would continue to do that all the way down. Now, do we always have to do almost no chance, some chance? No, I could have done it by female or male if I wanted to as well. There's something called conditional distribution, which leads us into. A conditional distribution of a variable describes the values of that variable among individuals who have a specific value of another variable. There is a condition that we're putting it on. For example, I might say, given it is a male, how many feel like they have no chance? So the condition is that they're a male. In other words, I can ignore all the females. I'm specifically looking at males. To examine or compare conditional distributions, you're going to select the row or column of interest. Am I interested in males or females or chance of getting rich? Use the data in the table to calculate the conditional. Using the marginal distribution, we're going to use that, and then make a graph using a side-by-side or what we call a segmented bar graph. So here's an example. This time I'm specifically talking about males. There's my condition. So of the males, we've got 98 out of the 2,459, or 4%, that feel like they have almost no chance. Whereas for the females, 96 out of the 2,367 is 4.1%. How does conditional distribution come into play here? Because I'm specifically saying of the males. In other words, I can ignore this column piece of data right here. Oops, I'm actually interested in the males. So I can ignore the females and specifically look at of the males, how many have almost no chance? And then you go through and you break down your percents that way, and then you go and turn it into a graph. Now they talk about a side-by-side bar graph, so I might have a bar graph that looks something like this, where here it's males, here it's females, and then we've got no chance. So then I would have a bar here and then a bar here with a key off to the side saying this is males. Filled in would be females. So this would be my female. That's a side-by-side bar graph. So I can compare them that way. And then now at the bottom, this would be no chance, some chance, very good chance, a 50-50 chance. So then they'd be next to each other. There's something also called a segmented bar graph, and a segmented bar graph breaks it into segments. Notice we've got 1, 2, 3, 4, 5 segments, all with a key off to the side here, so we know. The difference here is that both male and female, the bars must go to 100%. Notice these both go to 100%, but then I can quickly compare the two. When I look, I can look at this and go, all right, well, they're about the same for almost certain. Purple is about the same. Green is about the same. Ooh, orange. Females feel like there's some chance. Less males feel like there's some chance. Males and females are about the same for almost no chance. So I can look at it quickly just straight across. But again, we've got categorical. Here's my males. Here's my females. But it's broken into segments. Reaches or both bars make the 100%. Or line up at the 100%. And then within the bar, this light blue, which is males that are almost certain, that is this piece of data right here, males that are almost certain. Purple is males that have a good chance. That would be this percent. So I'm just adding these percents up to make 100%. So I can compare them easily if they're right next to each other. Organizing a statistical problem. You'll see this throughout the book, and it's not a bad idea. The AP stats test people, when they go to grade your test, will love this scenario. As you learn more about statistics, we got to find a way to organize our thinking. State, plan, do, conclude. State what the question you're trying to answer. Plan. How will I go about answering the question? What statistical techniques does this problem call for? Do I need to look at the median? Do I need to look at the mean? Do I need to look at a bar graph? Is it quantitative? Is it qualitative? Then, do I make graphs and carry out needed calculations? Do that. Then we need to make a conclusion, or we want to go through and analyze the data, give your practical conclusion in the setting of the real real world problem. And we want to analyze the data. But we really are going to follow through this year: state, plan, do, conclude. If they see that on your test, it's very easy to organize. You write state, write it out. Plan, write it out. Do, write it out. Conclude, write it out. The AP graders will love that, and they'll know that you're already on task, and I will as well, since I'm going to grade like the AP people. Not a bad idea to help show us that you know how to organize your thoughts. All right, in section 1.1, what did we learn? The distribution of categorical variable listed categories and gives the count of, or percent, either one, of individuals that fall into each category. We talked about the difference between pie charts and bar graphs, and they're both dealing with categorical data. We talked about a two-way table, which has two categorical pieces of data, or variables. We talked about row totals and column totals, and how we can start to talk about marginal distributions. Those totals go in the margins. That's why we call it marginal distribution. And then there are two sets of conditional distributions for a two-way table. We've got the row data, and we've got the column data that we're looking at. We also learned about side-by-side bar graphs and segmented bar graphs. To describe the association between row and column, we can compare an appropriate set of conditional distributions. Even a strong association between two categorical variables can be influenced by other variables, which we call lurking. We'll get into that more in another chapter. But keep that in mind, that there are other variables out there that we should keep in mind that might have an effect on these things. But that's all we have to do, is simply say there could be other lurking variables, and if we can pull some out, that would be great. We need to organize our thoughts, and in order to organize our thoughts, we've got the state, plan, do, conclude scenario that you want to put out on your paper, and then write out for each one of those what your thoughts are. That finishes this section. In the next section, we're going to move on to dots plots, stem plots, and histograms, and start looking at quantitative data. I hope that helps. That's the end of section 1.1. Good luck with your homework.